All right. So our final is Friday, May 8th, 11 a.m. to 12:50 p.m. If you already have too many finals on that day, or for some other reason you want to take the final on a different day, email me. We should be able to accommodate that. I just got to make sure that I have enough chairs in each room. Some of the rooms get like really full when everyone shows up. But usually it works out. So we are continuing our final exam review today. So I've been posting all the recordings where I've been listing what questions we've been covering. I think we may have hit them all by now, but not necessarily all of them in each class. So what question would you guys like to look at from the final exam review? 20. It's an excellent one to look at. All right, so we have here a log equation. Log base 4 of x minus 5 equals 2 minus log base 4 of x minus 11. So we are solving the equation. That means we are finding x values that when we plug in those x values, it makes the equation true. So in order to solve log equations, when we have more than one logarithm, we need to get all the logarithms on the same side and then use log properties to condense them down to a single log. So first thing I'm going to do is add the logarithm on the right over to the left side. Now it's real tempting when you see the logs vertically like this to add the insides, but that is not what happens. So I would just rewrite them. So when I have the sum of two logarithms with the same base, log base 4 of A plus log base 4 of B, then I can combine this into a single log. Now logarithms change operations, so I'm not going to add the insides. I'm now going to be multiplying the insides. So I have log base 4 of x minus 5 times x minus 11, and then that all equals 2. Now that I have a single logarithm, I can get rid of the logarithm. So what undoes log base 4? What cancels out? How do I get rid of that log?
Exponential.
Yep, we're going to convert to exponential. So if I use an exponential function on both sides, and since it's log base 4, I'm going to use 4 as my base. So 4 to the log base 4 undo each other. So I just have x minus 5 times x minus 11. And then on the other side, 4 to the second power is 16. So I moved my logs to the same side. I used my log properties to get one single logarithm. Then I canceled out the logarithm by using the exponential. Now I have a quadratic equation. To solve a quadratic equation, I need that equation to equal 0. Right now it's equal to 16. So it's really tempting looking at this line to be like, oh, x minus 5 equals 16 or x minus 11 equals 16. No, that does not work. because there's more than one way I can multiply stuff to get 16. There's too many ways, an infinite number of ways, in fact. I need this to equal a 0. 0 is the only magic number that I can set things equal to. So I'm going to have to FOIL these two binomials out. So I'll have x squared minus 11x minus 5x, and then plus 55 is equal to 16. Now I want this to be a 0 on the other side, so I'm going to minus the 16. And then I'll also combine like terms. So I'll have the x squared. Negative 11x minus 5x is negative 16x, or minus 16x. 55 minus 16 is positive 39. Now I have a quadratic equation equal to 0. Now I can factor and solve, or I could use the quadratic formula. Either method will work. But the numbers are deliberately picked, so they will factor. And in fact, there's not a lot of choices for multiplying to 39. It is divisible by 3, and it is in fact 3 times 13. So 3 plus 13 is 16, but I want these to add to be a negative 16, so I got to make both of these minus. Now that I have a product equal to 0, the only way two things being multiplied equals 0 is if one of the two things being multiplied is 0. So either x minus 3 equals 0, or x minus 13 equals 0. And then I solve, I add the 3. So I have x equals 3. And I add the 13. So I have two solutions. Now, for most equations, when you finish solving, the solutions are your answer and you're done. With log equations, though, or any equation that has a domain restriction, so any equation where you're dividing by a variable, square rooting something, or logging something, you need to check your answers. Make sure that there's not bad math that happens. Now, we could also just figure out the domain restriction based on the original equation. But we can also just plug the numbers in. So we are checking 3 first. So 3 minus 5, this is log base 4 of negative 2. That is enough to throw out x equals 3. Now we're going to check 13. That was our other solution. So I substitute that in. 13 minus 5 is 8. So log base 4 of 8. That's good. And then 2 minus log base 4 of 13 minus 11 is 2. That's also good. So I don't know what those decimals are because they're not pretty numbers. Log base 4 of 8 is an ugly number. But it equals 2 minus log base 4 of 2. All I care about when I'm checking is that the number inside the logarithm is positive. Once it's positive, that means the solution we were checking there is our solution. So that's why we throw out x equals 3, because it gave us the log of a negative number. In fact, it did it twice, because over here, it would be the log of negative 8. So at like twice over, we throw it out. Yes, the 3 is getting thrown out because it made there be a negative inside the log. And we can't take the log of a negative number, just like we can't square root a negative number. We also can't take the log of 0, but it's very rare for you to plug in a number and get 0. Like that won't be a solution to an equation typically. All right, what's another one we can take a look at? Number 10. All right, so number 10 here is giving us a quadratic trig equation to solve. So our whole goal is to get theta by itself so we can say what numbers theta can equal that will make this equation true. We do get the added caveat that we only need to carry about solutions between 0 and 2 pi, which that's just a way of saying solutions on the unit circle. So I'm trying to get cosine squared by itself. Now, if there was an extra like cosine theta, I'd actually have to deal with this like a quadratic and do some factoring, but there's only the single term with theta in it. So I can just solve this. So I'm going to minus the 5 on both sides. So 8 cosine squared theta equals 2. And then I divide by the 8. So we have cosine squared theta equals 1/4. Now we're trying to get theta by itself. There's a cosine attached to that theta, and there's a squared attached to the cosine. So my next thing to get rid of is the squared. I'm going to do that by square rooting. But what else do I have to remember when I square root? Yep. So I actually have two equations that I'm going to get here now. I have the cosine of theta could equal positive, the square root of 1/4 is 1/2, or I have the cosine of theta could equal negative 1/2. Now this is where we're going to look up on the unit circle where the cosine of theta is 1/2. So remember, cosine is the x coordinate. So the x coordinate is a 1/2 when it's close to the y-axis, so that's pi over 3. So we get pi over 3 and 5 pi over 3. That's where cosine is positive 1/2. And then cosine is negative 1/2 on the left side, which is at 2 pi over 3 and 4 pi over 3. Now, technically, all of these are plus 2 pi k. But if you don't write the 2 pi k, that's okay, because our actual solutions are the 4 numbers we just got, all 4 of them. So a normal trig equation, when we solve it, has two solutions. When we solve a quadratic trig equation, a quadratic also normally has two solutions. So we actually end up with 2 times 2 solutions, 4 solutions to the quadratic trig equation. We do have one like this on the test. It is free response. Now, if you forget the negatives, you'll still get most of the credit.
I have a question.
Mhm.
Is it still 2 pi k even though it specifies x within 0 to 2 pi?
You don't have to write the 2 pi k. So if you don't write it there, totally fine. I'm not going to take off points for that. I was just saying, like, technically that's the spot where it would go. But yeah, if we plug in k equals -1, we'll get negative numbers. That's too small. K equals 1, everything will be bigger than 2 pi, so they're too big. And when k equals 0, we just get the numbers we got from the unit circle. So if you just write those 4 solutions, that's fine. All right, let me yoink 15. All right, so 15 has a graph attached to it. But we're not actually going to have to worry about the graph on the exam. It was just, this was the only question I had that asked about the domain. So all we have to do on the test is just worry about the domain of this crazy little function. So the domain comes from whatever is inside the logarithm. The domain restriction for logarithms is the inside must be positive. So that means the x minus 4 must be greater than 0. Which then I add 4, and I have the inequality x is greater than 4. And I do my number line. Greater than 4 is everything to the right, all the way up to positive infinity. And it gets an open circle because we don't have an equal bar. So our interval notation would be from 4 to infinity with parentheses everywhere. Now, when it asks for the vertical asymptote, we get that by setting what's inside the logarithm equal to 0 or taking the boundary number from our domain. So the vertical asymptote, is x equals 4. Now, our particular graph has some transformations here. So the x minus 4 means we're going right 4. And the plus 1 means the graph is getting shifted up 1. Now, the original logarithm graph goes through the point 1, 0. And looks like that. So to the left of that point, it's hugging the y-axis. To the right, it lazily shoots off towards infinity. Now, when I do my shifts, right 4 and up 1, my new graph, if I shift my 1, 0 point, my graph is going to have to go through the point 5, 1. And if I look at my graphs, there should only be one point, one graph that goes through 5, 1. Now, the other thing to account for is that negative in front is going to do a flip on the graph. It's an outside the function, so it's going to flip y values. So I call that an up-down flip because it's flipping the top and the bottom. So now it's going to hug the asymptote, but it's going to hug the asymptote on top and then shoot down to negative infinity. Or, well, yeah. Negative infinity for the y values, positive infinity for the x values. Yeah, for mine, the graph that matches is C. That's the only one that's going through the 5, 1 point. But all you have to worry about on this one for the test is just the domain. And I think this one is even multiple choice. All right, what's another one to look at? Number 9. So number 9 tells us, given that tangent of theta is 2, and theta is between 0 and pi over 2, use the double angle identities to find the exact value of the following expressions. So my sine 2 theta and my cosine 2 theta, those are formulas on the formula sheet. So when we look at the formula for sine 2 theta, that is 2 times sine of theta times cosine of theta. So I need to know what sine of theta and cosine of theta are in order to answer what sine 2 theta is. Now they go to the effort to tell me theta is between 0 and pi over 2, which is just telling me that theta is in quadrant 1. So if they go to the effort to tell me theta is located somewhere, then I'm going to go to the effort to draw the triangle. Now they told me tangent of theta is 2. But I've got my right triangle drawn. And since it's a right triangle, my right triangle trigonometry can come into play. So I need to label my sides. So what is our diagonal side of the triangle called? The side that's opposite the 90-degree angle. Yep. All right, what about our vertical side? Yep, that's opposite theta. And then that leaves our horizontal side as adjacent to theta. So we got to remember how these side names get interacted with our trig functions. So this is our hippies. Some old hippie caught another hippie tripping on acid. So tangent is O over A. Now my tangent is 2, so I'm going to sneak in an over 1, so I've actually got a position for both things. So that means my opposite side over here is 2, and my adjacent side is length 1. Now I can solve for my hypotenuse, so that way I can figure out what the sine of theta and the cosine of theta are, so I can use those in my formulas. So Pythagorean theorem, a squared plus b squared equals c squared. So we have 5 equals c squared. We're going to square root and remember our plus or minus. But since this is a hypotenuse is always positive. We're also in quadrant 1 where everything is positive. So our hypotenuse here is the square root of 5. So I want to write down what is the sine of theta and what is the cosine of theta. So sine some old hippie OH 2 over the square root of 5. Caught another hippie AH 1 over the square root of 5. Now don't worry about the square roots. The formula will take care of those square roots for us. So when I'm filling out sine of theta, I know sine of theta is the same as 2 over the square root of 5. This is not theta is 2 over the square root of 5. 2 over the square root of 5 is a ratio of two sides. Theta is an angle. So the sine of theta, the whole expression, sine theta, can be replaced with 2 over the square root of 5. Likewise, the cosine theta can be replaced with 1 over the square root of 5. And then my formula had that 2 in front. So now I'm just going to multiply. So that is 2 over 1. So 2 times 2 times 1 all on top is 4. 1 times square root of 5 times square root of 5 is just going to be 5. So my sine 2 theta is 4/5. Now on the test, we're not going to ask for both sine and cosine. But that's just the way webwork worked. On the test, it's also not going to be a quadrant 1 angle. It'll be somewhere else. So you got to pay attention to if that third side is positive or negative. Now the formula for cosine 2 theta, there's 3 of them. But in this case, I usually go with the first one, which is cosine squared theta minus sine squared theta, since I already have both sine and cosine. And now I'm just going to fill those in. So each of those are squared, and then we're minusing them. So 1 squared is 1, square root of 5 squared is 5, minus 2 squared is 4, square root of 5 squared is 5. So 1/5 minus 4/5 is negative 3/5. So our cosine here ended up being negative, but the formula produced that negative for us. So we didn't have to think about what quadrant does 2 theta end up with. Should it be positive or negative? The formula just took care of that for us. So what questions do y'all have on how number 9 shook out? Yes, so the two formulas I pulled there, the sine 2 theta and the cosine 2 theta, those are going to be on the test. All the formulas that were on exam 3 are going to be the formulas on the test. And a full complete unit circle. And it's actually, the front page has the formulas, but the very back page of the exam has all the formulas, so you can also rip that off as a separate page. And then have it next to your exam so you can reference it easier.
If, um, if it were a different quadrant, how exactly do you go about determining the signs again?
So if it's a different quadrant, when we're solving the Pythagorean theorem here, and we've got the plus or minus, we just look at where theta is defined and see is the x direction negative or positive, is the y direction negative or positive, just based on where that theta is. That's the other reason why I always draw the triangle in the quadrant they tell us, so that way the direction of my sides reminds me of whether they're going to be positive or negative. All right, what's another one we can take a look at? Which one? 8, yes. All right, so the format on 8 is a little bit weird because it looks like it's multiple choice, but it's actually a checkbox. So there could be multiple correct answers here. But then I've got an x and I've got a 3 pi over 4 as my two angles that are being subtracted. And then I'm taking the sine of that. So what I need to use to evaluate this one is I need to look up my formula for sine of a minus b. So let me write that down first. The sine of a minus b is sine a cosine b minus cosine a sine b. This will be on the formula sheets. You don't have to remember this formula. You just have to know to go look for it and make sure you write it down correctly, because it's very easy to make a transcription error from the formula sheet onto your paper. All right, now I'm going to write the actual problem down. Our formula was sine of x minus 3 pi over 4. So everywhere there's an a, I'm going to write an x. Everywhere there's a b, I'm going to write 3 pi over 4. Now on the exam, this one is going to be multiple choice, but not this matching bullshit. So one of the answers will be correct and the other 3 answers will be wrong. Now it turns out on this matching one, most of the answers are actually wrong, so it ends up being pretty similar feel to a multiple choice. Now, we'll look for this one first. So sine x cosine 3 pi over 4. I've got cosine x sine 3 pi over 4 and then a minus. Nope. D is not the same. And then f sine x cosine 3 pi over 4 looking good, but then they put a plus. So nope, not f. Now all the rest of them have values filled in. So the cosine and the sine of 3 pi over 4, I can actually look those up on the unit circle. So 3 pi over 4 is in quadrant 2. So the cosine in quadrant 2 is negative. Now our pi over 4 reference angle, that's our square root of 2 over 2 triangle. Sine in quadrant 2 is positive, so that's positive square root of 2 over 2. All right, so my first two answers have the wrong formulas. They've got the 1/2 and the square root of 3 over 2. Those are the wrong numbers. So now I've got C and E. Well, I look, I've got a negative and I've got a minus. C there has pluses, so it's not C. E, I got a minus, a negative sign, and a minus. E works. So E is our answer here. So the test is going to look real similar to this. The angle will be a little different. And then when you're solving a question like this, it really is crossing off 3 of the answers, therefore the 4th answer must be correct. And there isn't a none of the above solution, so one of the answers will be correct. Now, on the multiple choice, you don't have to show your work. So if you can just look at it and like reason your way through to the answer without showing work, I'll give you credit for it. Some of the questions like I can do without showing my work, so I'll make the assumption y'all can too. If you randomly guess and pick the correct answer and don't have any work, you will also get full credit. But if you guess and you get the wrong answer, then you're not getting any credit unless you show me some work. If your work shows you were making good progress towards the answer and you just made a mistake somewhere, then I'll give you some partial credit on the multiple choice. And of course, on the free response, you always get partial credit for writing something. Do you want me to work the other half of 8? Because 8 had 2 problems, or is that good enough? Cool. All right, what's another we can look at?
Exponential properties one where we solve for x with different cases.
Yep, that is 18. All right, so my equation 2 to the 4x plus 3 is equal to 3. Now, there is no way to turn 2 into 3 or 3 into 2 without involving a logarithm. Now, the directions here specifically say type an exact solution in terms of natural logarithms. So what that means is the very first step here, I need to use a log so I can move my power down in front of the log. That way my x is actually on the line and then I can solve for it. The directions, when they say natural logs like that, that means the log that we want to apply to both sides of the equation is the natural log. Technically, we could use any log here. We could even use log base 2 or log base 3, but webwork is only programmed to understand the answer in terms of natural log. So again, our log properties take the power and say bring it down up front. Now the power is a whole crazy thing, 4x plus 3. So I'm going to bring that down with parentheses. And then that is being multiplied by the natural log of 2. And this equals on the other side the natural log of 3. All right, so now my x is on the line. I'm just trying to solve for it. Couple of ways to go from here, but what I usually do is the natural log of 2 and the natural log of 3, that's something I could type on the calculator and the calculator would spit out a number. So this is really just a number times 4x plus 3. So if this was like a 7 out here, I'd distribute the 7 through. So even though it's natural log 2, I'm going to multiply that weird natural log number to both of the pieces. So I'll have 4x times the natural log of 2 plus 3 times the natural log of 2. And then that still equals the natural log of 3. Now, in order to get my x by itself, I've got stuff being multiplied to the x, and then I've got a thing being added over here. So before I deal with the multiplication, I'm going to deal with that added term by subtracting it to the other side. So now I have 4x natural log of 2 is equal to the natural log of 3 minus 3 natural logs of 2. Now the 4 and the natural log 2 are both attached to the x by multiplication. So to get the x by itself, to keep the x here, I've got to get rid of the other stuff. So I divide by the other stuff. Whatever I do on one side, I do on the whole entire other side. So I now have x by itself. And that ridiculous thing is our solution. Now, certainly that is something I can type on the calculator and get a decimal for. And if you give me the decimal on the test, that's fine. In fact, when we got the 4x plus 3 times the natural log of 2 equals the natural log of 3, if you wanted to write the decimals in place of natural log 2 and natural log 3, you could. I'll take that result. But for web work, we have to keep it in terms of the natural log. The numbers here, though, are all very arbitrary. Like, they showed up in places and then we just kept moving the places around, but those numbers could be anything and the whole process is identical. Now, there are different ways to write the answer, but this is generally the answer most people get. Now, it's real tempting to see the natural log 2's there and want to cancel them, but they don't cancel because I have subtraction on top. I could only cancel out natural log 2 if it was being multiplied to everything on top, with the multiplication as the outermost operation. Subtraction is the outermost operation right now, so I can't do any cancellation. All right, do we have one more we want to take a look at?
Excuse me.
Go for it.
What if it was? What if the negative 3 ln2 was in front, we still couldn't cancel?
We still couldn't cancel. We'd have to be able to factor natural log of 2 out of the whole top.
Ah, okay.
So it'd have to
So
be
if it
part of
was
both.
so if it was ln4,
It doesn't factor that way. Like,
ah,
you can rewrite natural log 4 so it's written in terms of natural log 2, but you're doing that using log properties. It's not because it's 2 times 2. It's because it's 2 squared, which I know is like saying the same thing twice, but it is different. Like the fraction here, what I could do if I wanted is split the fraction. And now this fraction on the right has the natural log 2 over natural log 2 with only multiplication. So here I could cancel. So another way to write the answer is the natural log of 3 divided by 4, natural log of 2, and then minus 3/4.
so is it the top half is basically in parentheses,
Always.
and
Anytime
that's
you
why
write
we
a big
can't
algebra fraction.
and that's why we can't cancel.
Yeah.
But we could split it and then cancel.
Yes.
Oh, that's so strange. Okay.
After I split it, now the outermost operation on top is multiplication. So I have 3 times a thing divided by 4 times the same thing. So now I'm just like reducing the singular fraction.
But uh it's a totally different answer if it's natural log 3 minus 3/4.
Yes, the natural log of 3 minus 3 all over 4 is not the same decimal as our original answer here.
Ah, okay.
Like if you type that on the calculator, it's not the same. These 3 answers, though, what I have here, these are all the same decimal, though. I got to be careful about typing them in the calculator because that 4 natural log 2 on the bottom, like you've got parentheses around the top and parentheses around the bottom. So typing it in can get a little weird. But those are all equivalent answers. All right, I've still got
Okay.
office hours today. And I'll have some tomorrow. All right, let me hit stop on the recording.